He is currently leveraging quantum computing tactics for healthcare analytics, such as EEG-based brain signals analysis. And he has interest in developing hybrid quantum classical machine learning frameworks and their application to biological and neural data. Today, he will present us about exploring quantum machine learning in healthcare, a hybrid quantum classical approach to EEG sleep staging. His presentation is based on the paper Hybrid Quantum Classical Neural Network for Automated Sleep Staging using EEG signals. Then let's welcome Jaewon Chung to the stage. Please share screen.
Can you see the screen well?
Yes, I can see your screen. Where?
Okay, then I will begin my presentation. Okay, hello everyone. It's very nice to meet you. My name is Jaewon Chung, and today I have the privilege of reviewing a highly compelling paper which is titled Exploring Quantum Machine Learning in Healthcare, a Hybrid Quantum Classical Approach to EEG Sleep Staging. While quantum computing might seem far removed from our daily clinical work, this paper bridges the gap in a very practical way. So let's start reviewing this paper. Before we dive into the specific architecture proposed by the authors, I want to briefly introduce my background and the reality of biomedical data. During my sleep research at KAIST, and I also did a summer lab intern in biodata science lab at NTU in Singapore, I spent a lot of time grappling directly with these kinds of complex biosignals. As you can see on the slide, this was a sleep automatization tool that I was developing through MATLAB. As you can see, classifying sleep stages isn't just about looking at a single wave. It requires continuously tracking parameters like theta or delta ratios of moving epoch by epoch and identifying the exact time points where stage shifts occur. So this is highly nonlinear, high-dimensional projection of the human brain's activity. The reason why I selected this specific paper is to explore whether emerging quantum models can finally alleviate the immense computational and manual burden that we face as researchers in the biosignal processing. Okay, we all know sleep is very essential for human health, making accurate sleep staging crucial in the researcher's perspective. However, the traditional gold standard relies heavily on polysomnography, encompassing continuous EEG, EOG, and EMG data streams. According to the AASM guidelines, these streams are divided into 30-second epochs and categorized into distinct stages, which you might have heard before, which is wakefulness and light sleep divided into N1 and N2 stages, and deep sleep stage and REM sleep stage. From a clinical workflow perspective, the critical bottleneck highlighted here is that this manual labeling process is very time consuming and it requires a lot of specialists to engage in this job. To automate this, classical machine learning has made significant progress. However, as anyone who has trained deep learning models on large EEG datasets knows, classical models inevitably hit scaling walls. Deep CNNs and RNNs often rely on brute force matrices to map these nonlinear biosignals. And as the dimensionality increases, models face severe overparameterization, where fully connected layers grow quadratically with the number of nodes. The consequences of these classical bottleneck are extended training times, a higher risk of overfitting, and profound difficulty in capturing subtle cross-channel dependencies. To overcome these limitations, the paper shifts the paradigm toward quantum computing. And I will first admit that my background is more rooted towards in healthcare and data science and not quantum physics. But as a researcher, what fascinated me is that treating quantum mechanics as a powerful new computational tool. Superposition allows the representation of multiple basis states simultaneously, while entanglement provides non-classical correlations across qubits. Also, variational quantum circuits act as trainable quantum feature maps for complex boundaries. We are already seeing quantum opportunities expanding in bioinformatics. For example, models like MSleepNet utilize hybrid networks for sleep arousal detection, and quantum-inspired instructors are used for complex fibromyalgia detection via ECG signals. They succeed because they extract nuanced details that classical models miss. So these followings, as I mentioned in the earlier slide before, can be accounted as the advantages that quantum computing devotes in the era of biohealth data. What I appreciated really much about this paper is that it is very straightforward with the current limitations of the NISQ method. Current hardware faces strict constraints, which is the limited number of available qubits and strict restrictions on quantum gate depth and high susceptibility to environmental noise. So fully requiring on pure quantum neural network is impractical. Instead, the paper proposes a pragmatic hybrid approach, which is a classical deep learning for what it does best, feature extraction, and quantum computing specifically for high-dimensional mapping optimization. So basically what they're trying to do is trying to extract the advantages of both the classical method and the quantum computing method and to unite it into a better method. To navigate those hardware constraints, the researchers propose a HQCNN architecture. The overarching philosophy is divided and conquer. The framework consists of three main stages. First, an adaptive CNN handles hierarchical feature extraction from raw EEG signals. And secondly, BILSTEN network captures bidirectional temporal dependency. And finally, the quantum layer replaces traditional fully connected layers utilizing VQC for high-dimensional mapping and classification. So let us break down the classical component. The architecture consists of 4 convolutional layers followed by max pooling and dropout. A critical engineering challenge in biosignal processing is data heterogeneity, especially differing sampling rates. The authors address this beautifully through an adaptive design. For a low rate of 100 Hz, small kernels are used to rigorously preserve fine-grained temporal details. Conversely, for a high rate of 200, larger kernels and strides are applied to effectively capture global features without overwhelming the system. Okay, then let's skip to the sequence learning. Following the CNN, the feature maps enter the BIOS system. From a clinical perspective, sleep stage transitions, they're not random and they're governed by physiological rules, which is influenced by both the preceding and subsequent epochs. A standard LSTM only looks at the past, but through this method, we can see the full temporal context, which makes it easier to predict the next sleep stage. This module compresses the sequential context into a single learned feature representation vector of size 256. This high-dimensional space is now ready for quantum mapping. Then let's look at the next stage, which is magnitude encoding. Here, the paper addresses a massive dimensional bottleneck. If standard angle encoding were used, it would require 1 physical qubit per feature, which totals 256 qubits, which is currently impossible for NISQ devices. So the author's solution is magnitude encoding, and this technique maps normalized classical data directly into the probability magnitudes of the quantum state. Consequently, it achieves exponential compression, which maps the data points to strictly log qubits. So this successfully reduces the original 256 features down to just 8 qubits, which makes it possible to compute through our hardwares. And these 8 encoded qubits then enter the variational quantum circuit. The researchers utilized a hardware-efficient ansatz with 15 trainable parameters. To train this circuit classically, they rely on the parameter shift rule, evaluating gradients via microscopic gate shifts. So crucially for the readout, they utilize an ancilla-based measurement, extracting Pauli Z expectation rules, which significantly reduces disruptive interference on the main quantum state. And this is the result and analysis and the conclusion part of reviewing this paper. To validate this model, the authors implemented the architecture using the penny lane quantum framework. The models were trained for 50 epochs using the Atom optimizer, which was explicitly targeted for NISQ intermediate scale hardware. They tested the model across multiple diverse datasets, which includes Sleep EDF 78, which is composed of 100 hertz and FPZ-CZ channel, and the ISRUC S1 and S3 datasets, which are consisted of 200 hertz and those channels that is written in the slide. And if we look at the results from the research they derived from this paper, we can see that the results are very promising. The HQCNN achieved robust performance in classifying W, N2, N3, and REM stages. However, the authors did explicitly report that limitation occurs in this method, since the N1 classification accuracy remains very low. As someone with EEG research background, I find this limitation very understandable rather than an entire flaw of the model. N1 is inherently a very transitional stage, so it can just seem as both stages, and it possesses subtle overlapping EEG characteristics with the waking stage and N2 stage. So even for researchers, it is very confusing to classify which is which. And the brief duration creates a natural class imbalance. So a lot of human experts also frequently disagree on N1 scoring, making it very fundamentally difficult for any sort of classification methods. And despite there are some challenges and limitations regarding the N1 staging method, the most compelling finding of this paper is the massive parameter reduction. The parameters required for the quantum layer are approximately 1/3 of what is needed for classical fully connected layers. And this is possible because parameterized rotations are highly compact. More importantly, entangling gates like CNA or Toffoli add absolutely zero trainable parameters to the model. The complex data correlations are achieved naturally through the physical nature of quantum entanglement, not through brute force computation. This paper successfully demonstrates that integrating classical sequence learning with quantum feature mapping offers a highly powerful, parameter-efficient solution for clinical biosignaling processing. It proves that we don't really need in-depth physicists to leverage quantum advantages in the healthcare AI. And this would be my review on the paper, and thank you for listening.
Thank you, Jaewon for the insightful presentation. Does anyone have any questions?
In this paper, there was no mentioning of this being tried on actual device, but since this paper was published in, I assume, 2023, I assume that the research will still be ongoing to be tested on actual devices.
If there are no more further questions, we will move on to our next speaker from the US. Let me introduce our journal club presenter, Matteo Moessner. Matteo is co-president of UC Quantum at the Pritzker School for Molecular Engineering, University of Chicago. He is currently leading quantum initiative and research within the university community, and he has interest in the intersection of mathematical and statistical physics. condensed matter theory, and quantum information. Today, he will present us about a generalization of heralded noise, quantum error correction to nilpotent topological orders. His presentation is based on the paper Stabilizing Non-Abelian Topological Order Against Heralded Noise, Biological Lindbladian Dynamics. Then let's welcome Matteo Moessner to the stage.
Great. Can everyone see the screen?
Yes, I can see it.
All right, fantastic. So, thank you, everybody. Um, my name is Matteo, and today, as mentioned, I'll be talking about my research on generalizing Heralded noise quantum error correction algorithms to nilpotent topological orders. Um, and so, two big caveats. The first is I'm going to be presenting this in a way that'll make it seem like I knew what I was doing from the start, which I definitely was not. The second thing is, um, this is it was a very mathy project, and I tried to make it as non-mathy as possible to make it accessible. But at a certain point, I will have to bust out some algebraic topology. So I'm sorry in advance, and I'll try to like be specific about what you should be taking away from that. Um, so first off, um, what is a Torah code? So Torah code, it is a lattice where you have two um two qubit sites, one at a vertex and one at a plaquette. Plaquette being the dual vertex in the face of the lattice. Um, and the way it works is that excitations at the vertex and the plaquette um, interact in such a way that's called braiding, such that their information is no longer stored locally. And that's what makes topological quantum computing, in theory, so powerful. Of course, never been realized yet, but here's hoping Microsoft can do it. Um, now, notice that the way it would work is that with the vertices, you have an orientation at every edge, and so if you multiply along all the edges, you should get nothing. It's in a sense the discrete version of Gauss's law. You multiply along the orientation of all the edges, no charge should go to zero. If you do have an excitation at one of the oriented edges, so that it flips, then you do have it no longer just goes to one, you have a charge. And similar thing with the plaquettes. And so these are the kind of errors that we'll be dealing with that will be relevant later. Okay, now the most important thing you have to understand for a lot of the rest of um, the Torah code is a thing called a stabilizer formalism. So essentially, um, at both the vertex and the plaquette, you want to choose an operator that checks if you have a valid code state. In a sense, like does is it trivial? If if there's an excitation, then the stabilizer will pick it up. Go, oh no, something's wrong, something's wrong. Um, and we'll see later that this will raise a flag in the system, and that leads to our quantum error correction algorithm. Um, and so how does this work? So essentially, um, at every plaquette or every vertex, if you apply the vertex or plaquette operator, which is on the last slide, and you don't get back the plus one eigenvector, um, then the code does that it raises a flag, and it can track these strings. And it can do so because heralded noise is specifically an erasure noise where we know exactly where it is found. So like at the vertex specifically. Um, and so the idea is the code checks along the strings or the plaquettes, and it will iteratively um, shorten the string of the excitation, the error, and then once it meets in the middle and it's isolated, it's eliminated. Um, and so that's why we want the noise to be isolated. Want to know where it is, so that we ensure that this shortening via the flags does work. Um, now, so the Torah code I've been showing so far is based on abelian representation, which is to say that the plaquette and the vertex operators commute, and we don't really have to worry about any weird stuff happening um, when you have them interacting. Um, then, if you want to instead um, form a representation of a non-abelian group, well, you can't they don't commute anymore, or don't necessarily commute anymore. So, um, what Sarong did was that he took this generalization of the plaquette operator, where the vertex operator remained unchanged, and you add this CZ gate. Intuitively, it makes sense, right? You have um, a phase or an excitation that could exist at a neighboring edge. You, if that exists, then the non-commutation will add a phase to the plaquette. You know, it's not a great explanation, but it makes sense enough. Um, and for the average physicist like Sarong, it was perfectly okay. And so he's able to just work with it, and you can make this error correcting scheme where okay, you try to shorten the path, and you do so, but then you have these entangled pairs um, where you still have to check again if there's not any more errors that are caused um, by performing the shortening algorithm. Um, and it works because it's localized. Now, how exactly do we do this for any other non-abelian group? That wasn't exactly clear. Um, and and that was what Saran Gopalakrishnan at Princeton wanted to work on. And that was where I came in. And so my project was figuring out how exactly do you describe what the plaquette operator and what the general lattice model should appear like for any non-abelian group representation. Um, so let's first talk about um, what non-commutativity actually does. So I mean, we're not working with the Pauli matrices here exactly. When I use X and Z, your mind goes to them. It isn't. We're actually working with the Lie group elements, the representation on the lattice. And for that, you need to take the Pauli matrices, which um, generate the Lie algebra, and you need to do the exponential mapping. It doesn't make, if you're not familiar with that, don't worry about it too much. All you need to know is that the Baker-Campbell-Hausdorff formula gives us this very pesky way of explaining um, non how to combine the x and the e to the y if x and y don't commute, and it's just this long list of commutators. And how do you know if it terminates? That's a great question. The thing is that there is one kind of group that we know it will terminate for. That is nilpotent groups. Um, And so a nilpotent group is a specific kind of group where there's a descending sequence of normal subgroups, which just to say like invariant group, like you perform conjugation by any element of G on the subgroup, it's still in that subgroup. Um, that's what invariant means. And so specifically, these normal subgroups are commutators. And so, as you can see here, through successive iterations of commutators, we eventually reach trivial com commutes. Great. So we want nilpotent groups, right? Um, cool. What do we do with that now? Okay, so take D4, which is nilpotent of order 2. So this first commutator, XY, it is central in the group. So we can just take it out of the big sum there. Everything else goes to 0. And so we just have e to the 1/2 commutator XY. And this is just adding a phase, okay? Um, and when I say U1, this is unit to a group of order 1. Um, that's just phases on the circle. So e to the negative I phi 2 pi over n, whatever. Um, so that's just all we're doing here. Um, okay, interesting. So that does explain why we were adding a phase to the CZ, but it's not specific enough. But see, that's where something interesting arises. If we then try to see how associativity plays into this, we then see that the phase has to respect this relation, um, which this is then something called a two cocycle. And this is unfortunately where the algebraic topology comes in, so I apologize. Um, okay, so D4. It's order 8. Okay? So that means that we have um 3 qubits, right? Because 2 to the 3, that's 8. You describe it, and we describe them cyclically through RGB. Okay? Um Now, as we have this sequence, um we can describe how much of R remains in G. Um Almost like the dependence of G on R. Um, you know, if we have abelian groups, it's always trivial. There's no dependence because everything commutes. It's fine. But because we have non-abelian groups, there's non-trivial dependence. Now, if we take the dual um qubits here, uh, we can define the dual cyclic relation, um, which is then B maps to G maps to R dual. We're specifically under the Z action for reasons I cannot get into. If you're interested, look up twisted field theories. Um, and so describing the dependence of R under the preimage is something we call the cohomology. And so the collection of all the cohomologies of a group with coefficients in a specific module. So in this case, U1, because our phases are U1. We call this the cohomology class of H to the I of G U1. Um, yes. Um, and so listen, if you don't know what a short exact sequence is, don't worry about it too much. Just know Z is normal in R under abelian group. under abelian addition. Then U1 is the quotient group of our Z. And so through algebraic topology witchcraft, you can make your the ith cohomology group of G and U1 is isomorphic to the I plus 1 cohomology group of G with R. And G with R is very easy to analyze because you can just look it up on groupprops.com. It's makes your life a lot easier. And so, okay, we mentioned that D4 gives rise to the two cocycle, which in this case just means that you have um, a two sequence. So like RGB, going from R to the G to the B, that's what it means. And so want to look at H2 D4U1. And so by what we previously showed, H the second cohomology group, actually, sorry, that should be the third cohomology group of D4 with R. It's isomorphic to Z2. That is um the the group with only 0 and 1 as its elements. Um, so a qubit. Um, okay, so if if no one got anything from what I said from the past, like 1, 2, or however many minutes, just know this is the important part. This is describing how we how this residual like dependence or traces um works. Because now as you go from R to G, um R has non-trivial dependence on G via the dual action. Um but it's only up to G. You don't have to go further than that. Um it doesn't rely on B at all. And so, okay, this gives us an insight as to how we should be approaching um adding a decorator to D4. And you know, next one in the sequence, it would be um the green of adjacent um adjacent edges on the plaquette. Um and to describe that phase operation, we use CZ. If there's an error, it will add a phase. And yeah, as we can see, this lines up exactly with what Sarong had for his initial plaquette operator. Great. Seems like we have a a good way of formalizing how to approach um generalizing these plaquette operators. Um, okay. All right. This is some more algebraic topology nonsense. Um, okay, essentially, only to know is that if we have a group that's a central extension, so essentially like take D8, okay? Um, it's isomorphic to or to D4, the group we've already been talking about, direct product Z2. Um, where Z2 is in the center of D4 and D8. And so what this suggests is that the action of GA on G, the quotient of G on G is trivial. And so, okay, the cohomology group just collapses. Um, so since D8 is essential extension of D4 by Z2, um, um, it collapses down. So every single um, dihedral group, the D's, um, they all just they all have the same cohomology group. Great. That that was easy. Um, and actually, that's a little bit of a typo. It's D8, D16, technically the same group, and so are D4 and D8. It's depends on if you want to describe them as what you define the dihedral groups as D of 2n or not. But I I meant to say so. I meant to use D8 here as example of d to the 2 times 8, 16. So yeah, just divide the cohomology group there by 2, and that's fine. Okay. Um, and so then this helps us find a way to describe infinite groups potentially through residually finite nilpotent groups. So take the Heisenberg group, where its center is NZ, which that is atrocious abuse of notation. I am fully aware of that. Technically, the center is isomorphic to it um under well in Z its addition, in Heisenberg group its multiplication. Um, but all you need to know is that you essentially just get that to find a quotient. It's instead of being H over the field of Z, it's H over Z mod NZ. Um, and it has order n cubed, and so it's significantly easier to analyze because if it's Z mod 2Z as order n cubed, you can show has as many elements as D4. We're back something that we know how to deal with. Um, and so yeah, oh, sorry, I forgot to define it. So a group is rigidly finite if you can always find some way to quotient the group that doesn't destroy an element. So you can approximate the Heisenberg group by taking however many quotients of h of n and then taking the direct product of them. That will approximate how the Heisenberg group operates. Okay, so then here's then the general procedure for how to generalize these Plaquet operators. Um, so the nilpotency order determines the length of the chain you have to deal with and the cohomology class. Um, if if G is central extension or is truly finite, take the relevant quotient that makes your life easy. Um, and then remember this equation we derived. Well, derived. I didn't I didn't derive it in front of you, but you can derive this. Um, that just look up on groupprops.com and you can or yeah, you can just look it up on groupprops.com. Sage could probably do it for you. And then based off that, choose corresponding C to the K Z decorators for the Plaquet operator. So each example, take the quaternions, also order 8 like D4, also nilpotent of order 2. Um, but it's its relevant cohomology class is H2, but that's isomorphic to Z2 direct product Z2. And so there you actually have to use CCZ to describe the the proper interaction of Q8 with its adjacent um, qubits. And yeah, I mean, this is just a little note on the specific lattice model. If you let G be of order n and you let P be the perimeter of the plaquettes, the only constraints you need are the max conjugate class has to be less than or equal to the perimeter of the plaquette, and n has to be less than or equal to uh, p minus 1, um, just to make sure that everything's well defined and you don't get like fluctuate or fluxes or interactions that like go back in on themselves. Um, that part isn't the most interesting thing. Just wanted to mention it. Um, yeah. Um, yeah, that's there's there's more detail relating to the specifics of how the error-correcting scheme is generalized via these duplicate operators and the higher Nilpotent orders. It's just needlessly complicated. The main point is just know that you modify the duplicate operators via the CD decorator, and that describes the non-abelianness interaction of nearby edges. Thank you.
Thank you, Matteo Moessner, for the insightful presentation. Does anyone have any questions?
So your work only works for groups that has nilpotent order?
Um, yes. Um, yes, the main point is that you need specifically residually finite nilpotent groups. Um, in order for um the uh the non-abelian interactions to not get out of control, and then you can't really define a proper lattice model with Tor code and the well, everything you'd want it to have. There's technically a model that works for any solvable group, um, which I know Ruben Veresen at U Chicago worked on. The main issue with that is that you can only really define it with qubits, or you can only make it nice after it's already braided to some degree. Whereas for this, the nilpotent residually finite, it always works, no matter how the anions are start braiding.
Is the number of cochain same as the order of the nilpotent order? Like
Sorry?
for example, so for D4 you have uh H1 and H2 so you have cochain 1 and cochain 2 for group D4, right?
Um, co- oh, sure, yes. Yeah, for D4, the relevant cochain is the two cocycle, cochain. And
Two
so
cocycle.
you're yeah, so you want the second cohomology group. Yes.
Mm, is that analogous to the fact that D4 has nilpotent order of 2?
Yes, that's exactly
Okay.
hold on. I where yeah, yes. The potency
Mm,
order and determines cocycle chain and the cohomology class. There's a general procedure. Like it I mean the issue is that you can show it through the BCH formula. It just gets very complicated for higher order ends very quickly. Um, the proper way to do it is through something called, again, twisted field theory, which I just did not want to get into today because then no one would understand what's going on.
okay, so for those finite group G, we have to change the placket stabilizer to add control Z gates. So is the yeah, how about the decoding procedure? Like is the decoding procedure, do you also study how to decode these error correcting codes?
Um, oh, yes. Yes. So yeah, the hardest part is how to generalize um this placket operator. Because um the way you describe the decoding mechanism is something called a leaf and a loop operator. Um which like you put into a Lindbladian and um it Um, and it does the whole like checking for if there are any flags are up or not. Um, so but like once you have already described how the Plicat operator um is generalized, it's fairly straightforward to describe how the leaf of the loop operator change. Um, but they're fairly complicated equations. Um, and so for the sake of brevity and clarity, I didn't want to include those. All right, any other questions?
If there are no further questions, we will move on to our next speaker from Singapore, Verma. Let me introduce our journal club presenter, Verma. Dev is a master's student at the Nanyang Technology University and a member of Professor Mark Go's groups at CQT at NTU. He is currently conducting research on quantum modeling and its various applications, and he has interest in quantum agents and their application to quantum game theory. Today, he will present us about extreme dimensionality reduction with quantum modeling. His presentation is based on a paper of the same type to extreme dimensionality reduction with quantum modeling. Then let's welcome Dave Verma to the stage.
Yeah, is my screen visible?
Yes, I can see where.
Okay. So perfect. So yeah, my name is Dave, and I recently started my master's at NTU, and I am working in Prof. Mile Gu's group, who is based here at NTU, CQT at NTU. And the paper that I'll be presenting today is called Extreme Dimensionality Reduction with Quantum Modeling, and it came out of NTU and a couple of other groups, and it came out in late 2020s. And the main claim is quite bold. It says that for certain families, certain family of processes, a classical model needs an unboundedly large memory to simulate them accurately. But a quantum model can do the same job with a single qubit, no matter how complex the process gets. So I'll spend most of my time building up to why that's surprising, and then let's see what the implications are. Yeah. So first, we begin with the setup. And the setup is this, that whenever you're trying to predict the future of some stochastic process, you need to store some information about the past. The question is, how much information do you need to store about the past? For something like a Markov chain, the answer is simple. You only need the current state. Memory is bound, finite, done. But some processes have long range dependence, and the future doesn't just depend on what happened recently, it depends on things that happened arbitrarily far back. And as you track more and more history, the number of distinct situations you might be in, and therefore the number of distinct things your memory might need to store, it just keeps growing. And that is where that's the regime where this paper lives in. And the question is whether quantum information can give you a fundamentally better way to handle this situation. So let's make this more precise. The framework uses something called the epsilon machine, and we borrow it from computational mechanics. The idea is that we group all possible histories by whether they lead to the same future distribution. If two pasts are statistically indistinguishable going forward, they get the same overall label. And these equivalence classes are called causal states. The epsilon machine is a minimal classical model. It's optimal in two senses simultaneously, where C mu is the Shannon entropy of the memory distribution, which captures the average bits you need in an ensemble setting. And D mu is the log of the number of distinct states, which captures the dimension you need in a single shot setting. And when we move to the quantum case, we replace classical states with quantum states. CQ becomes the von Neumann entropy of the memory density matrix, and DQ becomes the log rank. It's essentially the dimension of the Hilbert space. And it's been known for a while that CQ can be strictly less than C mu. This paper is really about DQ. Specifically, how much less can that be? Which, as I just mentioned, is the dimension of the Hilbert space. Okay, so what sets this paper apart from some of the earlier work is that for Markovian processes where future only depends on the present state, there's a finite number of causal states, so memory is bounded anyway. And quantum advantages here are real, but the gap d mu minus dq is always a finite constant. For non-Markovian processes, the epsilon machine can have infinitely many causal states, and d mu can diverge. And earlier work had shown one case where dq could beat d mu without bound, but it required an infinitely large output register, which is not practical at all. So this paper was the first to show that an unbounded dq advantage using only 2 qubits in total in the single shot setting with no ancilla of growing size. And that is what makes this practically meaningful. So I've been talking about a non-Markovian process. So next, I would like to describe the non-Markovian process that this paper talks about. That process is called the dual Poisson process. And the setup is simple. There's a system that emits events through one of two hidden channels with rates gamma 1 and gamma 2. After each event, the channel is reselected at random, probability P for channel 1 and 1 minus P for channel 2. And an external observer just sees when an event happens, not which channel is fired. An example of this could be atomic decay. And here, phi of n is the survival probability. The chance that a gap between consecutive events is at least n time steps long. And it's a mixture of two geometric sums. And here's why it's non-Markovian, because as time passes without an event, the observer updates the belief about which channel is active. And but that belief depends exactly on how many time steps have elapsed since the last event. So the history length that matters is unbounded. Every distinct elapsed count n is its own causal state. And that is what we can see in figure 1. The epsilon machine is an infinite chain. So what happens to the classical memory as you try to model this more and more precisely, as you start to shrink the time steps? The conditional future distribution is different for every elapsed count n, so you can't merge any states without losing predictive accuracy. And the epsilon machine, as I mentioned before, already has infinitely many states. So d mu is infinite at any finite time step. Just as a reminder, d mu sort of captures the number of distinct states that we need to store in our classical memory. Now you might say, okay, let's try a truncated model. We merge all states beyond some cutoff n term. But as you refine your time step, longer and longer gaps become probable, and you need to track more states to stay accurate. And this truncation threshold n term has to grow like one log of 1 over delta t. So both the truncated c mu tilde and d mu tilde diverge, which you can see in figure 2. Two classical lines, as you'll see, just keep climbing as precision increases. So how do we do it with quantum memory states? So a qubit lives on a Bloch sphere, which has infinitely many points. So in principle, you could assign a distinct quantum state to every causal state n without ever needing a larger Hilbert space. And the explicit construction, which you can see in equation 4, each memory state, zeta n, is a single qubit state whose amplitudes depend on the survival probabilities. The property is that consecutive states are non-orthogonal, they're close but distinct, and as n grows, they all converge towards the zero ket, which is clustering near the North Pole. And classical models need orthogonal states for each causal state, but quantum models don't have that constraint, and that's the resource that's being exploited here. And since the process isn't memoryless and a qubit is the smallest possible quantum memory, this model is optimal for a single shot setting. And this is where dq equals 1 exactly. So how do we actually do it? You have two qubits, a memory qubit that stays in one of the zeta n states, and a blank probe qubit that is initialized to the 0 ket at each time step. The unitary U acts on both. After U is applied, you measure the probe. If you get 0, the memory qubit automatically transitions to zeta n plus 1, which is inching closer and closer towards the North Pole, and the elapsed count goes up by 1. If you get 1, the memory resets back to zeta 0. An event just happened and we detected it, and the measurement outcome is the output symbol for that time step. It is important to note that U is the same used at every time step. It doesn't need to know what N is. It doesn't need an external counter, no classical side channel. And from figure 3, you can see that the architecture is just the same 2-qubit block repeated. And U decomposes into at most 15 single qubit rotations and 3 CNOT gates, regardless of the process parameters. And that matters because it's in reach of the current hardware. And so what is the main result? The main result is that for any dual Poisson process at any level of precision delta T, there exists a quantum causal model with CQ at most 1 and DQ at most 1. And once again, we look at figure 2 and we see that the two classical lines diverge without bound as you zoom into finer and finer time steps, whereas the two quantum lines stay flat. DQ stays exactly at 1 and CQ is actually less than 1. And the gap between classical and quantum grows without bound. There's no precision at which classical catches up. And that is the extreme dimensionality reduction of the title. And this is quite experimentally relevant because every previous result showing an unbounded quantum memory advantage either needed many simulators running in parallel or an output register that grows with the required precision, neither of which is quite practical. Our construction only needs 2 qubits, and that's it. But and memory state preparation is just 3 qubit single rotations, 3 single qubit rotations. U is at most 15 rotations and 3 CNOTs. And both of those are within the gate sets of current ion trap and photonic systems. And photonic experiments have already demonstrated sort of this kind of compression for 3 causal states into a 2D memory. And verifying this advantage, we just need to count the dimension of the memory system, which is much easier than performing full state tomography. And there are a few open questions and few caveats. And the biggest one, which I feel is quite a distinctive feature of quantum research, is that this is a very specific result for a very specific process, which is the dual Poisson process. And it's not a general theorem that says, oh, quantum always beats classical without bound for non-Markovian processes. We are not quite there yet. So the construction is quite elegant, but it's also very heavily tailored to one particular family of processes. Second, the optimal quantum encoding for arbitrary processes is still unknown. The states that I showed you, the zeta n states in equation 4, they are an explicit construction, and there may be better encodings out there. Third, the problem is that in the continuum, that delta t goes to 0, where divergence is fully realized, but experimentally, you're always at finite precision. And the advantage is real at any fixed delta t, but you can't witness the full scaling in a single experiment. And another sort of important fact that I must raise is that current quantum hardware has fewer qubits at lower fidelity than classical systems have bits. So while the advantage is proven, classical hardware would outperform quantum hardware in terms of achievable precision today. Just to summarize, there are 3 things to take away from this entire presentation. And that is that classical models for non-Markovian processes with long memory can require unbounded dimension. For dual Poisson processes, both CMU and DMU diverge as you increase your precision, and no classical model can avoid this. Quantum models can do it in 1 bit, And the explicit construction gives CQ at most 1 and DQ exactly 1, which as we'll recall, is the von Neumann entropy and the dimensions of the Hilbert space for the qubit for our quantum system. And that is the ultimate compression limit. And the architecture is just 2 qubits, a fixed unitary, and standard gates. Ion traps and photonic platforms can implement these now. And that's it. Thank you so much.
Thank you, Dev Momer, for the insightful presentation. Does anyone have any questions?
For an n Poisson process, the idea is that this methodology is only for a dual Poisson process, and that is an open question that I guess maybe you and I could research on. Although I would assume that the construction pretty much remains the same, because what is really happening is that we have some events, and we are making predictions on the future distribution of these channels, that okay, this one is more likely, maybe channel n-1 is more likely based on what the events are. But classically, I think your dimensions will blow up, and quantumly, I'm not sure, but I would think that they remain the same.
Yeah, if there are no further questions, we will move on to our next speaker from the Philippines, Kai Karu Rasala. Let me introduce our journal club presenter, Kai Karu Rasala. Kai is pursuing his bachelor's and master's in computer science at the La Salle University of Manila, working with the Dr. Andrew L. Tan Data Science Institute. He is currently focused on the practical implementation of quantum frameworks, and he has interest in designing quantum algorithms and full-stack web development. Today, he will present us about efficient block encoding of dense matrix via QRAM using the QISCA frameworks. His presentation is based on the paper Quantum Resource Required to Block and Matrix of Classical Data. Then let's welcome Kyle Karurasala to the stage.
Hi, thank you for the introduction. So yeah, thank you. Just to note, this project is actually a group work from my internship during Q World Internship 2025. So we actually did this last year, and we are currently doing it right now. So it's not yet done. So you will not see any published paper regarding this, but most of the discussion that I will discuss today is mostly based on the papers that we gathered. Okay, so these are my group mates, Jaya Sharma, Kalpesh Bhatnagar, and Biraj Dosa. Okay, so I want to start this presentation on what Juan Miguel Arazola said. So I think Sir Juan is a part of Penny Lane. So you're gonna see this quote from the reference below. So he said, if I had to summarize quantum computing in one sentence, it would be this. So it should be information is encoded in quantum states and processed using unitary operations. So I want to emphasize here this specific sentence encoded in quantum states and processed using unitary operations. So as we know, there are certain limitations for quantum information. When we say quantum states, there are certain properties of quantum states. And when we say unitary operations, meaning there are certain properties for our matrices if we represent our operations in matrices, which is unitary. Okay, so the first part of what he said is actually information is encoded in quantum state. So maybe this is a review for all of us how we represent information in quantum. So for example, we have a classical information X. So you can think of this as an array. And then the question is, how are we going to encode this as a quantum information, or how are we going to convert this as a quantum information? So we know that in quantum information, we do expect that our data can be, or our information should be represented in this form. So it's a linear combination of bases. So the thing that I've mentioned earlier, where I said there are certain properties. So you can think of this as a restriction when you're converting from classical information to quantum information. So for example, there is what we call it should be a normalized vector. So every element in the vector, when you norm square that and then sum of all of the num squared elements, then it should be equal to 1. And then for example, you're using qubit. So most of the hardware implementations right now is in qubit. So it makes sense that we think of our algorithms, quantum information encoding in qubit format. So we know that we can have m qubit, and m is represented as the upper ceiling of log n base 2. So I would say that's a limitation. So just to give more example, just to give an example to make this clear, for example, we have a classical information where we have 3 data. So for example, x is equals to 1, 2, 3. If we convert it into quantum information, so we know m is 2 qubits, and 2 qubits is represented in 4 elements in our vector. So that means we have another one element, one extra element here. So that's why I said it's actually a restriction. And take note that it's not entirely 1, 2, 3. You actually normalized it. Okay, so that's how our quantum information works. So now in the second phrase of what he said, so processing information with unitary operations. So for example, we want to convert a ripple carry adder. So this is how we add in terms of classical information. So this is how we implement addition operation in our classical computers. But then if we convert it into a quantum operation, or let's say quantum adder circuit, then you can see that it's actually a bigger circuit, which means it's a little bit inefficient. But if you use this multiple times in your algorithm, then it would be very, very inefficient. So you can see that in classical, there's less bits, and in quantum, there's more qubits. So the number of qubits is greater than the number of bits. So yeah, that's one practical challenge for developing quantum algorithms. And if we actually look into the deeper level of how we represent operation, so we know that our classical operations can be represented into gates, logical gates. But then if we represent these classical gates into quantum gates, we have to think about how are we going to make it reversible. So this is coinciding to the property of classical operations to become a unitary operation. So when we say unitary operation, again, it means that we have a matrix U that if we inverse it, the dagger of U and multiply it to itself, then we should be able to get the identity matrix. So that's a very challenging limitation for us if we want to convert. For example, we have here a classical operator A. How are we going to convert it to quantum operator? So this will be the main topic of today's presentation, specifically my presentation. Okay, so just want to give you an overview of how are we going to talk about this. First, I'm going to talk about how this block encoding works. So block encoding means this is how we convert our classical operation into any to quantum operation. So you can think of operation in this sense as a matrix. So we can have any arbitrary matrix that can be applied to our quantum states. So how are we going to do that given that we are limited by the property of normal vectors as our normalized vectors in our quantum states and unitary operations for quantum operations. And then once we know that, we're going to convert it into a practical implementation using what we call QRAM. And this QRAM will be further used in a bigger implementation in what we call state preparation. And then once we have the state preparation, then that's the time that we're going to block encode certain operations, certain matrices from classical information. Okay. Um, yeah, so the question now is how do we encode an arbitrary matrix A? So meaning arbitrary, we're not going to restrict ourselves in unitary matrices. So how are we going to do this? Now, imagine that you have a matrix A. So you can think of any matrix, but then just to have a simplified explanation, you can think of this matrix as having real values and has an n by n size of the matrix. So the way we're going to encode this to become a unitary matrix, by the way, we want to denote this unitary matrix as U sub A. And then we place A in the top left block of U sub A. And take note that in this part, you can see that there is an alpha divided to the matrix A. So this alpha is actually the normalization constant. And take note the asterisk represents any what we call the ancilia elements or unnecessary elements in the matrix that is needed to encode the matrix A to become unitary. So these are what we call ancilia elements for our matrix A, matrix U sub A. So just to take note that you can actually place it into any other part of the block. So you can place A here, you can place it on the top right, lower left, and lower right. But then for simplicity, we just want to discuss how are we going to place it on the top left. Now, for example, we want to reverse um, the method that we are going to do in such a way that we have a unitary matrix U sub A, and then given this encoding, how are we going to extract A from it? So it was actually defined by this operation. So this specific part on the right-hand side of right side of the U sub A, it actually tells you that you have to remove unnecessary columns. You have to remove unnecessary columns. And then the left part of the left part of this equation, the left thing beside the U sub A actually tells you that you have to remove unnecessary rows. And then now you're left with A over the normalization constant alpha. So the only thing left for you to do is to divide it, multiply it to the normalization constant. So then now you have this matrix A. So this is your original matrix. And take note that I represented it here as approximation because given that you have these unnecessary elements in your matrix, the way you're going to encode it to a unitary matrix will make it not exact. So it's actually an approximation. And yeah, given that it's an approximation, you can actually define a precision. So this precision tells you the upper bound limit, upper bound error of the approximation of A. So take note that what we're doing here, so this part tells you that this is your uh, extracted A. So you have to to subtract it to the original A, and then you have to get the norm of that matrix. And then given that, you will actually get the error that you had. Okay, so take note that we are denoting here uh, U hat sub A. So this means that this is not actually exact representation of A. So this is an approximation. So if you're curious why this is just an approximation, again, it's because of the ancillas that we have. It's because the way we encode it. So probably division, precision errors, something like that. Yeah. So there are a lot of reasons why. So now, how are we going to turn this U sub A into a circuit? So again, coming from our encoding equation before, we can actually make it into a form like this. So we just transferred the normalization constant on the other side of the equation. So in that sense, we don't have to think about multiplying a certain specific constant to the circuit. How are we going to represent that? So we are just left with this one. So we need to think about the ket zero, the identity matrix, and then the block encoding of the matrix itself. So the way we're going to do that is we have to decompose it into a product of two unitary matrices. And then the contents of these matrices is actually uh, the UR prepares the n qubit in this specific state that we call psi sub j. And then the UL prepares the state phi j sub n. And then UR will actually have this encoding. So from the default set of ket zeros here, so that's the original state that we have, it will transform it to our target state. So let's call this our target state, this the ket psi sub j. And then we also have another target state from UL, from the transformation of UL that we're going to call or denote ket phi sub j. So what are these target states? So it's actually a part of our matrix, uh, unitary matrix U sub A. So once we are able to encode this, so we are actually separating some parts of U sub A into two parts. So one part going to the ket psi sub j, and another part going to the ket phi sub k. Okay, so there's actually reasons why it was actually implemented like this, and it's in this paper. Okay, so if we want to convert it into a circuit, so we just need to implement the U sub L and the U sub R. And take note that the U sub R here is in Dagger format. And if we further decompose it, we can actually see that inside the implementation, we'd have state preparation. So this is where the state preparation takes into account. And then we have a swap gate here. And then it's a similar state preparation, but in Dagger format. So take note that they denote different state preparation, target states. So which means the only different thing here is that you have different inputs. Okay. So again, we're done with the block encoding. So that's the strategy that we're going to do. but then we haven't deep dive into how we're going to implement the state preparation. And just mentioned earlier that to implement state preparation, we're going to use the concept of QRAM. So now I'm going to discuss to you the key concept of QRAM and how are we going to implement it. So first, we have to think about how QRAM works. So classical RAM query actually works like this. So you have an address I, and then given that I address, it will actually give you the data on that address I. But then in quantum computation, we want to query the data by using the entanglement property of our quantum computation. So let's say you have the address I, you need you want to entangle the data on address I on the address itself. So given that you have ket I, ket 0, so ket 0 will be transformed to the target data that you want, which is the data on the address I. So it's entangled to the address. Okay. So there are several ways to do this. And one implementation that we considered is the select swap. So in the select swap, based on the name, so it's the implementation is separated into two parts. One is select and one is swap. So let's deep dive into this. Take a closer look. So you can see here that we separated it into two implementations. So one again is for select, one is for swap. And then for each implementation, so for select, you have certain parts of the address. So this is your address register, your N. So you separate your address into two parts. The first half will be used for the select implementation. The latter half will be used for swap implementation. So the 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 wires that you see here below is actually it actually contains the data that you want to query. So it's like you have to divide your data into chunks. So for example, this first column is the first chunk of your data, and then this one is the second chunk, and then as we go, and then the select implementation, what it does is to select which chunk of data will you select. And then, for example, our address is 000. So it will toggle this specific Toffoli gate. And then once it activates, it will activate all of these gates. So take note that these are all X gates. And then it will uncompute this one. So this control qubit into going back to into its original state, which is ket 0. So now, given that it toggles all of these X gates, so you see that there's a bunch of ones and zeros here, but then you don't know which data you want to query because this one is a chunk of data that you got from select. That's where the swap implementations takes into account, where you just need to properly positions the data that you really want to query from this chunk of data on the top wire of this specific part. So this part gives you the data, and the only thing that you have to think about is what is the data that you will get on this specific wire, the topmost wire. Okay, so it take note that the wire actually denotes the number of wire. So that's the amount of data that you queried. So it's not just one qubit or two. Okay, now we have another implementation. It's called bucket brigade. This one uses the concept of superposition and the phase encoding. Okay, so first you have to implement a Hadamard gate. Okay. And then this is your address. You actually separate your address again into two. So the first address, the first part of your address is for uh, specifically toggling this one. And then the second part of your address will be further swapped here if your first address toggles this part. And then we'll think about this later in a few. This bucket, this BB0 gate. So we'll further look, take a look inside on it. So after that BB, so before we take a look into this, after the BB, it will actually uncompute. Okay, it will actually uncompute. Now, if we check the BB gate, the BB circuit, so it's actually complicated like this. But then uh, I think the important thing here is that you just need to think of this as a tree. It's a tree structure for our circuit. So for example, you start here at level 0. So it will actually uh, uh, converts or uh, places the data in the correct position. So for example, you have two options from level 0. It's either you go on the top or you go on the bottom. So it depends on the address that we have. So again, the address is coming from this one, the one where you swap it from your second half or the latter half of your address. So yeah, you actually get your data. You actually toggle this one, the Z gates. It's a bunch of Z gates. So take note that this Hadamard gate is passed down to this one. So you have this data wire. So that wire is it contains uh, your original state, which is in uniform superposition. And then once you get into this part after this tree traversal, you will actually get the phase encoding. So they're using Z because this one is in ket plus state. So once you toggle Z, it will become ket minus. And then that's how you get the data. Since after all of this part, this tedious part, you will actually convert it back to the Z basis. So you're applying Hadamard gate at the end. So you get either 0 or 1. Yeah. So last thing that I want to talk about QRAM is the load F. So load F, it's a bit different from the first two because you have an arbitrary state. It's not just 0 and 1. And take note, sorry, it's not arbitrary, but from negative to positive real numbers. So you can encode real numbers using this QRAM implementation. So it's not just 0 and 1. Okay, so I think the most important thing here is the V implementation, this one. So the V implementation is just a bunch of rotation along the y-axis. So again, this is similar to the concept of bucket brigade, where you just need to think about the topmost wire. So it positions the data that you really want to query on the topmost wire. So the input data here is in terms of real numbers. So you don't query in terms of 0 and 1, but you get a real number. Okay. To take note, in our select swap, you have a lot of garbage data here, but the only thing that you are concerned is on the topmost wire. For bucket brigade, you don't have any garbage data, so that's a good thing. For load F, you also don't have this garbage data. You get all ket zeros at the end. You just need to think about on the topmost wire. So now for we're going to use QRAM concepts for our quantum state preparation circuit. And the end goal of this state preparation, given that you have an array of coefficients, is that you need to encode it in this form. So again, the bottom part is just the normalization constant, which is just the norm of the entire vector. Okay, so and you need to think about your data in terms of tree structure. So it should be like this. Maybe I'll just proceed further for better understanding. So for example, you have to rotate uh, your qubits in the along the y-axis using this angle theta 1. So for example, you have a bunch of qubit. The first qubit you have to rotate it by this angle, and the way we're going to get the angle is using this tree structure. So the thing that I mentioned before. So theta 1, the first angle, uh, can be calculated using this. So take note that you're actually dividing this into the norm of the entire vector. I just simplified it to this tree structure. So you have to see this. You have to use this for your first angle, and then use this on your second angle, and use this on your third angle. And the pattern follows as the tree grows. Yep. And then, for example, we have n equals 4. If we actually check it, then we can actually get the encoding for that specific basis. So for example, for basis 0, 0, you will get this coefficient, which is what we actually want. So we are able to encode the elements in our array in terms of rotation along the y-axis. And the angle is represented by this one. Okay, so the question now is, how are we going to do this? So there are several ways. There are two ways actually, which is the fixed precision and the pre-rotated. So in fixed precision, it works like this. So it looks like this. It's just a bunch of RY rotation on just one specific wire. I mean, it's just this wire. It's not just one, but this specific wire. And then the important thing here is that you define how much precision that you want to get. So more precision means more qubits. So the trade-off is between the number of qubits and the amount of precision you need. Yep. So if we further look in the circuit of S sub 2, you actually see this one. So it's a bunch of, again, rotations along the y-axis. Sorry, this RY gate denotes this one. It's the same RY gate. And then this is the actual S sub P gate. So it properly positions your qubit address. So it knows that which rotation along the y-axis should be implemented. Yep. So for the entire state preparation circuit, it's actually like this. You have to use either the bucket brigade or select swap, and then sandwich the state preparation circuit between the two QRAM implementation. So it's either you use bucket brigade or use select swap. Yep. So for pre-rotated, this one has fixed precision, so it's different implementation than from fixed precision. So this is your entire pre-rotated gate. I will just deep dive how you implement this SPF. So this SPF is just correctly implementing the the reason why we say that it's pre-rotated, since we have to use the load F QRAM. So this is the last QRAM implementation I've talked about. So after this implementation, you will get a lot of angles here. So a lot of qubits rotated along the y-axis. So um, you just need to properly position those angles in the right order. So that's what the SPF circuit does. So this is your entire pre-rotated state preparation. And then this flag is just for uncomputation so that you don't have a large garbage data. Now, so you're going to use this pre-rotated or fixed precision using the block encoding strategy that I've talked about. So you see that this is, for example, you use this as your U sub L circuit, then you just need the U sub R dagger circuit. So you can do that as well in the fixed precision. It's either you use fixed precision or pre-rotated. Yeah. So the reason why we're implementing this in QISC is QISC is actually a good quantum computing framework. It's a library that is actually built using that you can use in Python. So it works as a similar to Qiskit, and it's I would say it's higher level programming since they introduce variables, basic operations in quantum circuits such as multiplication and addition. So you don't have to manually implement it on your own. You can use asterisks and plus symbols to implement these operations. But then they still allow you to change those operation implementations. So for example, you want to change implementation for multiplication, then that will be still allowable for this specific library. And then you can also convert this CRISP code to OpenQASM or Qiskit code. So if you want to run it in a quantum hardware, then it would be very flexible. Then, the CRISP framework works actually like this. So you have this variable quantum, and then it is being managed by the quantum session. And then you have this quantum circuit that is actually from Qiskit. So I think the CRISP is actually built using Qiskit framework also. So they just wrap it around and then make it more higher level programming. Yeah. So I think that's it for my presentation. Thank you.
Thank you, Kai Carl Rosala, for the insightful presentation. Does anyone have any questions? If there are no further questions, this concludes the presentations for today's joint club. Thank you all for your active participants. Thank you.